Some problems are simply too complex for today's computers. And the strange thing is, it isn't because the machine is slow. It's because there are simply too many possibilities to sort through, more than any amount of raw speed can rescue you from. That idea is the doorway into quantum computing. So let's walk through it properly. At a basic level, almost everything a computer does comes down to one task: exploring a large number of possibilities and finding the right one. Planning delivery routes means trying different paths. Designing a drug means testing different molecules. Cracking encryption means checking different keys. It all works the same way. But here's the problem. Add just a few more variables, and the number of possible outcomes doesn't grow gradually, it explodes. From thousands to millions to numbers so large they quickly become impossible to process. And that's where classical computers hit a wall. So scientists asked a different question. What if, instead of checking possibilities one by one, you could work with many of them at the same time? That question is the foundation of quantum computing. Why quantum? Because it's based on quantum mechanics, the physics that describe how nature behaves at the smallest scales. At that level, things stop behaving normally. Particles can act like waves. They can exist in multiple states at once, and they can become linked together in ways that don't exist in the everyday world. Quantum computing doesn't ignore these rules. It uses them. The idea goes back to the 1980s. Physicist Richard Feynman realized something important. If nature itself is quantum, then simulating it properly might require a quantum computer. So what makes a quantum computer different? It comes down to the smallest unit of information. A classical computer uses bits. Each bit is simple: 0 or 1, off or on. Everything your computer does is built from those. A quantum computer uses qubits, and qubits behave very differently. A qubit isn't just 0 or 1. It can be both at the same time. A simple way to picture it: a classical bit is like a coin lying flat on a table, heads or tails. A qubit is like that same coin, but spinning in the air. While it's spinning, it isn't just heads or tails, it's both at once. Now here's where things get interesting. When multiple qubits work together, they don't just store one possibility. They represent many possibilities simultaneously. But there's a catch. The moment you measure the system, it collapses to a single result. So the real challenge is, how do you make sure the result is the correct one? This is where quantum computing becomes powerful. First, there's entanglement. Qubits can become linked together so strongly that they behave like a single system. Then comes another key idea: interference. Quantum systems behave like waves, and waves can combine. They can reinforce each other or cancel each other out. Quantum algorithms are designed so that wrong answers cancel out and the correct answer gets amplified. It's like tuning a signal until the right answer stands out clearly from the noise. That leads to a fundamental difference. A classical computer checks possibilities one after another. A quantum computer shapes all possibilities together so the right one emerges. Think of it like guessing a password. A classical computer tries one option at a time. Try, fail, try, fail. A quantum computer explores many possibilities at once and uses interference to make the correct answer stand out. So why don't we have quantum computers everywhere? Because they are incredibly difficult to build. Qubits are extremely fragile. Even tiny disturbances can introduce errors. To make them useful at large scale, we still need more stable qubits, better error correction, and much larger systems. This could take years, possibly decades. And even when they're ready, they won't replace your phone or laptop. They'll be specialized machines for specific types of problems. Things like discovering new drugs, designing better materials, building more efficient batteries, or fundamentally rethinking encryption. We're still in the early stages, and no one knows exactly where quantum computing will have its biggest impact. But one thing is clear, this isn't just a faster computer. It is a completely new way of solving problems. And if it works at scale, it could expand the very limit of what humanity is able to solve.